Section 13.2, line integrals, video 9, line integrals in space. We're going to do one that is our line integrals with respect to x, y, and z, which are similar to the ones in 2 dimensions with respect to x and y. And our curve is going to be 2 line segments connecting the points 2, 0, 0 to 3, 4, 5, and then to the point 3, 4, 0. Now we can't just assume that these are collinear. In fact, if you drew a picture, you can see that they're not. There are other ways to check that they're not collinear. So we're going to have to think of this as 2 separate paths, not drawn to scale. 2, 0, 0 to 3, 4, 5 to 3, 4, 0. Actually, this representation is good because it would be right below it. It has the same x and y coordinate, just different z coordinates. And both of these would be on the xy plane because z is equal to 0. So this actually isn't that bad of a representation. All right, so we're going to have to break this down into 2 smooth curves and parameterize each. So let's start with curve 1. Now we haven't talked about how to parameterize a line in 3 dimensions, a line in space. But it's just like parameterizing a line in 2 dimensions. You have 1 minus t times the initial coordinate, so 2, 0, and 0, plus t times the terminal coordinates, which are 3, 4, and 5. So if we clean these up, so the bottom 2 are easy because of the 0. This is just 4t and 5t. For the x function, we have 3t minus 2t is t, and then we have a plus 2 when we distribute the 2. For the second curve is actually pretty easy. In fact, we're going to parameterize this a little bit more intuitively, because think about the directions that we're going. The x and the y are constant. X of t is equal to 3, y of t is equal to 4. They're not changing. It's only the z function that's changing. But we can define this as z of t equals t, as long as we define our endpoints correctly. Now here's where I have to abandon normal interval notation, or this is less than or equal to t is less than or equal to that. Our t is starting at 5 and ending at 0. So this is going to be defined from t equals 5 to t equals 0. And so when we set up the integral, the lower limit of integration will be 5 and the upper limit will be 0. Now if that's confusing you, and my apologies, I need to go back to this one and define our interval. In this approach, it's always t is between 0 and 1. And if this intuitive approach to defining the second part of the curve parametrically is not sitting well with you, then I invite you to go back and redefine all 3 of these the same way we did before. The first 2 will come out the same. The bottom one will be different, but it will be from 0 to 1. But we'll get the same answers, because the curve is the same. How you parameterize is irrelevant. So let's start with the curve over C1. We're going to integrate from 0 to 1, because that's how we define our parameter, of y, which was 4t, times dx, the derivative of x is 1 dt, so that's easy, plus z, which was 5t, times the derivative of y, which is 4 dt, so also pretty easy, plus x, which is t plus 2, times dz, which is the derivative of the z function, which is 5 dt. So let's clean this up by first pulling out the dt and then just gathering all our like terms as we run across them. This is the times. So here we have 4t plus 20t, so we're at 24t plus another 5t, so 29t, plus the only constant term we have is the second half of this distribution, 10. Well, this is pretty easy. 29 halves t squared plus 10t from 0 to 1. The 0 annihilates the antiderivative. That's actually a correct word mathematically. And so we just have to substitute the 1. We'll get 29 halves plus 10. 10 is the same as 20 halves. So 29 halves plus 20 halves is 49 halves. Not our answer, but the first part of our answer. Over the second curve, and be careful, I'm going to use this one, but the initial value of t is 5 and the terminal value of t is 0. So this is being evaluated from 5 to 0 of, I'll set it up again, y is equal to 4 times dx, the derivative of x is 0. So we don't have to worry about that part. It zeroes out. Z is t times dy. Its derivative is 0, so we don't have to worry about that. And then x, which is 3, times dz, which is 1, dt. So this integral zeroes out a bunch of it before we do anything. So we're going from 5 to 0, gone, 3 dt. So it's 3t evaluated from 5 to 0. I know the 0 annihilates it, but it's the first part of the subtraction problem, so we can't just throw it away. 3 times 0 is 0, minus 3 times 5 is 15, it's negative 15. Therefore, the line integral, I'm going to be really lazy here. No, I'm not. The original integral of y dx plus z dy plus x dz is equal to 49 halves minus 15. 15 is the same as 30 halves, so 49 minus 30 is 19 halves. Again, this is an example from the book. It's on page 767. And they got 9.5. Tomato. All right. I'm going to have to pause this series of videos here for several reasons. Number one is it's a lot later than I expected to be right now. Number two, what happens next, I need to really look over before I jump into it because it's a lot of physics. It's about forces and work and things like that, which is not in my field of expertise. Mr. Walker, on the other hand, he does an excellent job of teaching that. If you want to get a head start on it, it's on page 768 where it says line integrals of vector fields. After all, the previous section was about vector fields. And there's a definition of it in terms of unit tangent vectors and position vectors and their derivatives. It's basically a formula and a setup, and it's not that difficult to do. But if I just go off the top of my head like I've been doing on these previous ones, I know I'm going to crash and burn. So I'm going to pause this and try to get some more videos recorded. They may not be in a classroom, they may be on a piece of paper at home. So I hope you're enjoying these videos. I hope they're helping. If you have any questions, please contact Mr. Walker.